Well, today on Standing on the Shoulders of Giants, we are here with Professor Lee Cronin, who is currently I believe you hold the Regius Chair of Chemistry at the University of Glasgow, among many, many, many other things. Lee, could you just give us a quick breakdown?
Yeah,
Sort of your background, if that's even possible to break down in a reasonable amount of time.
I'm English, living in Scotland in the UK. I suppose I've been a chemist. I'm still a chemist, and I love doing science. And my research group in Glasgow is, I suppose, the intersection between robotics, chemistry, origin of life, alien life, chemical AGI, chemical computation, computing. Basically, being a geek with electronics and also setting fire to stuff with chemicals is probably the way I describe myself at the moment, and trying to understand what reality is. So I also want to be a philosopher, but I'm not qualified to be a philosopher or actually a scientist, actually, but blagging it thus far.
I mean, given what you've done, I would say it's you're doing an at least reasonable job blagging it. So fantastic.
I do like occasionally having a good idea, and you're like, I don't think people give themselves much credit here and there. I keep trying to, I keep forgetting because I want to do the next thing. Sorry, I was interrupting you.
No, not at all. Was there sort of a defining moment in your career, in your life that took you down the current path that you're on? Was there a reason you wanted to get into sort of the science field, and what was that moment?
I don't think I can ever remember a time where I never really decided to be a scientist. I just kept asking everybody how everything worked, and they wouldn't give me satisfactory answers. And so I would say, well, why does that work because of that? Well, why does that work because of that? Why does that work because of that? And then I just took everything apart. I had a very, 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 I got bored extremely easy. So I just took everything apart. Got into everything, building chemistry sets, citizens band radio, wind tunnels. But I suppose it's really difficult to remember your earliest memories, but I can always remember when I must have been just toddler, I don't know, whatever age, maybe 4 or 5, maybe earlier, just at a seaside, and I cut my foot on a broken piece of glass. And it was painful when I remember looking at my foot and the blood, and I was like, so how does this work again? There's stuff coming out. I remember taking Coke bottles and turning them upside down and liquid coming out, and there's liquid coming out of my foot. And I know that's a bit bad, but it's not too much. And then it kind of struck me there that it probably wasn't that normal to look at your injury and go, why is that working? And that's always I've been. I spent ages playing around with marbles and refracting light. I tried to build my own CO2 laser once. I set fire to the shed, to the garage, because I didn't have any CO2. And I figured if I started a fire and I trapped it in a cylinder, it would be fine. But yeah, the cylinder was full of soot, so that didn't work. So I guess I've always been breaking things. And I'm just fascinated by the fact I could never put them back together. So I guess I couldn't be an engineer, so I had to be a scientist.
Why couldn't you be an engineer? That's sort of the path I took. So I'm curious why science versus engineering. Not that it matters.
Well, actually, I take it back now. I had to be an engineer, do a lot of science, but I think I'm a very good engineer with teams. So I tend to kind of break things and say, right, let's reconstruct it minimally. And then I love working with people that are good designers and good builders, and we kind of interact together. So I wouldn't say I'm not an engineer, but I think I'm better on the deconstruction than construction. So I love working with people to constructing things, then say, right, let's take it apart again and remove bits. And I'm a minimalist. I like to basically, do the minimum amount of work to get the minimum amount of function, and that's something that's always obsessed me. And I think that's probably why I got to Origin of Life, because I was just like, how does this stuff work? It's kind of like, you only have to plant a seed, and suddenly you have a plant or a tree, and I kind of always got fascinated by the intersection of how things worked, how things grew, and how to build stuff. But I was poor at building stuff because I couldn't get anything back together.
Okay. I can definitely relate. I mean, I took the telephone off the wall when I was like 3 or 4 years old, disassembled it across the kitchen floor, and I got I actually got a reasonable response from my dad on this one, which was, if you can put that back together and put it on the wall, because they were not happy, of course, when they saw it on the floor, and it works, then we're going for ice cream. If you can't, you're in trouble. So it was actually a pretty decent way of motivating, and on to engineering ever since then. So that
Right.
makes sense. So I can definitely relate. So as we were speaking about before we got rolling, you have something called the Chemputer coming out, or potentially already out. What is this? This is I've read some things about this, but I'd love to hear it sort of from your perspective. You know, where did it come from? What's it going to do, etc.
So the Chemputer was a concept actually that I came up with years ago. It was just the idea of I wanted to build an origin of life machine. We'll go back before that. Before that, I wanted to crack the origin of life, and I figured the origin of life was nothing more than a search problem in chemical space. So you go back to the beginning of Earth, there's chemistry everywhere, it's very simple chemistry. How hard could it be? Just get a bunch of chemists in the lab, some test tubes, mixing random stuff together, not asking too many questions. This is when I started getting into trouble with my colleagues, you know, when I wasn't allowed, when I was saying, no targets, just random mixing. And then obviously you can spend, PhDs are, you know, they're relatively long, not as long in the UK as they are in the US, but 3-4 years. And I was thinking the labor required to do the experiments wasn't going to work. And I said, well, I need some automation for this, but I can't afford the robots. So it was about 2010, 2011. So I started to put together a very basic kind of digitally controlled chemical reactor. So I had some pipes going into a chemical reactor, and I could rather than pouring in the liquids by hand, I could pump them in. I could turn on the stirrer remotely, so it would stir. Could turn on the heater, and so on. And I remember being interviewed by a magazine called New Scientist. It's kind of the
Sure.
Scientific American, yeah. So in the UK, and the guy was kind of discussing what I was doing. And then I got that interview led to another interview with a newspaper called The Guardian, so there's all these interviews happening because everyone got really excited about this mad chemistry professor making robots that didn't really work. And the reporter read the New Scientist article and said, "You're making this origin of life machine. I don't really get what you're making this other machine. It's kind of like a chemical computer or Chemputer." So he actually invented the term.
Okay.
But then in that way, or just characterize what we were doing. But really, in my head at that time, is I wanted to be able to write code, and that code was to control a robot to put in chemicals according to a recipe. So you have kind of chemical code. So on one hand, you have like a Python code, if you like. Back then, it wasn't in Python; it was in LabVIEW, believe it or not. So LabVIEW code that would turn on pumps and valves, and the abstraction that led to was those chemicals going in, and I could draw my chemical scheme. And so you had this LabVIEW code and this chemical code, and they meshed together. And so a computation is the act of taking a computer architecture that's well designed, a Turing machine or almost a Turing machine, having some kind of programming language, writing some code, you know, whatever it is, a well understood kind of data analysis algorithm, or maybe just reprinting some stuff, I don't know. And it works every time on any platform on the same machine. And I figured this was what was happening here. And it took me really 5 or 6 years to realize how to explain that, because what do computers do? They do computation. What do Chemputers do? They do computation. Because I kind of thought this was a bit of a bullshit term. And actually, the reason why I had to, because I started a company many years ago that trademarked the damn word, and the Chemputer, even though I was going to make the Chemputer, but they were never going to make it, they trademarked it. And every time I used the word Chemputer, they told me off. And I was like, oh, screw you, you can't trademark a verb. So it's computation. And I was like, oh my gosh, actually, what is computation? It is this specific, mathematically precise thing, but now it's different. Rather than be embodied on silicon, it's embodied in chemistry. And then I became more and more confident about developing the formal methods and the labeling and so on. And this is something I've been trying to say for 10 years, and actually been falling on deaf ears for 6 or 7 years of that. And what I was trying to say, chemistry is great. It can be encoded. Chemists have a schema. They have what's called an ontology. They have a relationship between what their atoms and bombs representation, and mix molecules together, get a reaction, make a drug, make a new material. Excellent. The problem with that is the individual has to have a certain amount of expertise, so there's a certain amount of knowledge, and there can be ambiguity. So not anybody could read that recipe and make that molecule. And I thought, well, why don't we just remove the ambiguity? And by specifying, everything like a good engineer, good chemical engineer, good scientist, because it helped make things more reproducible. And then the chemist kind of started to say to me, no, that's completely silly. You can't encode chemistry. Chemistry is too hard. It's not uniform. It can't be standardized. And I said, okay, that's fine. Let's pretend it can. And I continued on to build this base layer, because I was convinced the only way I was ever going to be able to do what we now call as artificial intelligence, do some kind of learning or understanding, is if we have clean and context data. And this is exactly what AlphaFold has benefited from, where you say you have protein structure. And why was that possible? Why is AlphaFold so magical? Well, it's not magical. It's just incredibly good machine learning, incredibly good architectures. And they benefited from two very important things, or three actually important things. Number one, protein sequence. Number two, protein structure. And number three, some constraints in the physics to basically go from sequence to structure.
And what is AlphaFold?
So AlphaFold is a program where you put in a protein sequence you could get, and it would predict the structure without you having to do a kind of imaging technique that requires crystals, or it's quite an expensive machine. So you can kind of guess the structure. It's a bit like if you were to make some origami in paper, but not fold it up, just cut it and make the creases. It would predict what the origami would look like, because you've cut the paper and you know where the creases are. AlphaFold doesn't replace what's called protein structure elucidation, but it accelerates that idea dramatically because of the clean data. And so biology was programmable because evolution invented the genetic code and the ribosome. Chemistry is programmable from the periodic table, but chemistry is a mess, which is not bad. It's great. It means we can do far more, but biology is really constrained. Chemistry constrained by the ribosome. So that's so in a way, the challenge I took on was ridiculous, but I think it's working.
Okay. So, and also, as we mentioned, is this being actively built?
Yeah, so the first Chemputer was it happened in many different sequences. So what happened was I designed the Chemputer in my head. I love designing things in my head. It's so easy. I can imagine it's there. It works. I went into the lab and I said to the lab, look, I've got this programming language that's going to run on this fictitious robot. Can you all start to play with the programming language? And they said, no, we don't see the benefit. And so I said, okay. And then this was in 2011, 2012. So I went away and went back and said, right, why don't we build some robots and then we'll think about the programming language. And I said, that sounds really cool. And the robots were quite expensive though, and they're quite modular, not modular, they were all vendor locked. You had to buy software and other software, and one thing wouldn't talk to another thing. And at that time, people started to play with, cheap 3D printers controlled by Arduinos typically.
Sure.
And I started to think, 3D printer has an STL code, which basically allows you to print the structure, the three-dimensional structure. Could I turn my motion into a static print? And everyone's like, what? And it's a bit like, well, I'm going to take my momentum space and put it into position space. And they said, we have no idea what you're talking about. I said, okay, look, if I 3D print a test tube of this size and bolt it to another test tube of this size and this size, I can pour my liquid in this end, fill it up, then pour more liquid in, it pushes it into the next one, pour more in, pushes it into the next one to the next one. It's a bit like Mousetrap, that game,
right,
right? Where you have all these things linked together, a bit like a fairground ride even, where you would go from one thing, connect to another one automatically, and you're you're literally on rails. So 3D printing the test tubes in the row puts you on rails. No one understood it. It was terrible explaining it. But my group were like, you bought us 3D printers. We're gonna 3D print Yodas. We're gonna 3D print, all sorts of crazy fidget spinners. And
Why not?
we might even 3D print the odd reaction. And so that got them thinking. So that was kind of the first genesis of the computer. I then basically started to think about commercialization. And the process of commercialization I went through, I got some money in the UK. It's quite hard back then. I mean, it's hard everywhere, right? Don't want to make excuses. I was lucky enough to get some investment, and the investors were like, "You're completely insane. We're not doing this, but we like the word. Thanks for the word." And they didn't believe I would make the computer work. So I raised money on grants, and I built it in my lab. So I learned to do software engineering, I learned to do electrical engineering, I learned to do mechanical engineering, I learned to do chemical engineering. And then by 2017, 2018, we had a working prototype. That was the first one.
Wow,
Yeah, that was in 5 years. Now we have 50 in the lab.
that's incredible.
Yeah.
And so this is formally commercialized at this point. I believe your company is doing these, correct?
Yes, I have a company called Chemify. So I kind of started that. I realized, and the previous company was great. They did a great job. They're still doing stuff. So, it's like when you start having companies like having children, you don't wish them many, you want to look after them, But what I wanted to do, my vision was really, although it's great to have a company, I really wanted to get the architecture out of the lab because I could believe it could make the difference to chemistry. That maybe, I don't know, this is sound really arrogant. I don't mean it, but I don't mean it to be arrogant. I just want to be. It could have the same difference to chemistry that the gene sequencing has had to biology, and that's
Pretty big. That's aggressive. I like it.
No, it's not. I mean, but basically, gene sequencing just allows biologists to make sense of proteins and things.
Sure.
And all I want to do is stop the chemists having to do all the manual labor and actually take a bit of code and run it. And gene sequencing and molecular biology is no panacea. Still, you still have to do some stuff. It still fails. But I figured I needed to find a way to create the architecture and then work out. And this was a thing where commercialization, I'm still on that journey, right? I mean, I'm in the middle of that journey right now. And a chemistry professor at the same time. So I'm kind of like, kind of got the benefit of both worlds in a way, or the misery of both. I guess it's not misery, but it's like academia.
It's challenging to say the least.
Yeah. I mean, look, in academia, it's great to get concepts, what might be possible. And if you want to innovate, it has to work. But actually, I really like innovating in industry or commercially because that requirement for practical implementation at a reasonable cost is what I need for chemistry anyway. Because I saw all these really expensive robots being built around the world. And so all these robots are one-off. And if they're one-off, there is no incentive to write a programming language and make a standard. It's like building HTML for when there's only one computer on the planet that can run it. As soon as you could run HTML on everything, and so I made a series of decisions when I was inventing the computer. First decision, I said, okay, it's going to run at the scale of a human chemist. So the scale that a human chemist works at, I'll make it work at because they will interact with it immediately. So it wasn't a huge vat or a nano thing. It was basically, good, cup size, right? A round bottom flask. So that was the first decision. Second decision, it was what's called a batch, where you turn a reaction on, pour the liquid in, pour liquid in, turn the reaction on, stop, do the next step. And I always wanted to do it this way. And one of the reasons why I got kicked out of mathematics at primary school, I think, was because I was obsessed with basically developing programming languages to cheat in math. And so I invented the computer like a kind of lambda, with a kind of lambda calculus in mind. I don't know if it's exactly equivalent, but I ended up in the kind of the learning difficulties class because I couldn't do maths. But I invented my own way of doing maths and programming. And actually, through the computer, I was able, I remember when I used to do this and how this works. And so I had this kind of architecture in mind, which was a state machine. So you have this, first of all, the robot was the size of a human, or not compatible with human hands, right? Not the size of a human. It was like just a little contraption in a fume hood, number one. Number two, it's a state machine. So you well-defined on, off states, Booleans, and all that could work. And number three, I only use the glassware that every chemist on the planet has access to with some minor modification. So the cost of the robot is literally probably not much more than the cost of what a chemist would use right now in terms of hardware. And that actually turns out to be really lucky if you want to scale a technology, because immediately all the chemists on planet Earth could potentially use this system and also take their existing lab notebook where they've been manual for the last, whatever years, and run it in the robot. So that means all the data they've been collecting, all the literature that was out there works. And what we've been doing in the company is kind of making like I shouldn't call it a large language model. It's not chat chem. It's like a large chemical model, which is able to basically, because I've taught it clean ways of doing operations, a bit like protein sequence, protein structure, magic bit in between, do the same thing.
Okay, so like for instance, if I wanted it to make me X, and you had the sort of the ingredients for X, it would effectively tell you this, and this, and then it would sequence it for you. That's effectively what we're talking about.
Yeah. So the way it works, you have to. So I don't like to use the word train because then people think it's a neural net. It does use neural nets, but before the neural net, you actually have to develop the architecture. I'm sure there are lots of people who might even be watching this or listening to this who are experts in deep learning, and all of us use the current infrastructure of the silicon revolution. So I would say, no silicon chip, no machine learning. It couldn't just happen magically. You need that architecture. So the temptation in chemistry and physics and in biology is to use machine learning on stuff when there is no architecture. And that means you're learning on weird things because you've got no standards. By having this system, we could then, because each chemical reaction has a sequence of turn the reaction on. When you turn it off, then you do a thing called a workup where you separate the components. Then when you've got the workup, you do what's then an isolation. And then after the isolation, you do the final step, which is purification. And this is almost like your Turing machine for chemistry. It only has 4 steps: reaction, workup, isolate, purify. Reaction, workup, isolate, purify. So with that in mind, then you can teach it, or rather than teach, just do chemistry in the literature in different classes. So chemists are taught lots of different reactions that will change particular types of atoms and bonds into other forms. And we get taught that. And there's like a finite number. It's a bit like learning a language where you learn a certain number of verbs. There's a certain number of actions in chemical reaction space you can learn. So what we decided, and you learn how to position them. So what we learned to do is we taught the system those verbs. Actually, it's quite a good analogy. It's not, the chemist will be shouting, "Oh, no, it's not a verb, it's a reaction." But it's a kind of, it's a particular circumstance. We turn the reaction on, add the reagents, heat, and then do all the extractions. So we did those. And then when we had a minimum coverage of chemical space, so we could go, it's almost like a maze. Can I go from here to here to here? Just needed to have enough knowledge so I could go through the gaps. Then when someone brings to me a molecule that has been made before, I can determine the route, like on Google Maps.
Right.
So, know anything. Or if I don't quite know it's been done before, I can guess the route and join up the dots through things I do know. And so you're right. And then you just put in that code and the robot just makes the molecule.
That's outstanding. I'm a big fan of that. Send me one when they come out. I'll try and figure out something to do with it. It sounds really interesting.
We have a portable version as well. The problem is when people come to the lab, I show them the big one because it's really easy to explain. Sure. And obviously Chemify is building products, right? And building not just software products and molecular dreaming products, but actually the hardware needs to look, even if we're not necessarily, distributing the hardware yet, we might be running it in-house, right? Who knows, right? But it looks fairly like the ENIAC might have felt, where look, that first electronic digital computer where there was probably the size of 2 warehouses and everything was blowing up. And it's not quite that bad, but it does look formidable. But what I've also built is a small version called the mini-puter. Well, actually, my student and then in the company we call it C3PU, which but it's this big. and it's much more tractable. And so it has a minimum set of infrastructure for pumping, for adding solids, for adding gas, and to temperature. And you can basically fit in a roller case, take it on an airplane anywhere in the world, and make stuff. Why would you want to do that? I don't know, but hey.
I mean, my product brain is going left and right in all sorts of different directions. Why you might want to do this? You could do almost like lab as a service type of deal, or you could sell these. There's a number of applications, at least in my own limited understanding of this.
So yeah.
Sorry, go ahead.
I was going to say, so exactly that. So I imagine that what we're going to do with chemistry in the end is we're going to go to server farms, right? So the other thing is, the other thing that everyone, because I'm in this middle, because I'm a really bad chemist, I'm a really bad programmer, I'm a really bad engineer. So when I go and talk to the chemist, he'll say, you're just shockingly bad at this. And I'm like, yeah, but look, this is cool. And you talk to computer science, it's like, you're terrible. But I kind of in this intersection where I was trying to explain to the computer scientists why I needed to take the description of the recipes and make a programming language, a Turing complete programming language. And all the computer science were like, yeah, of course it's Turing complete. Of course you can do this. And I was like, but no. What you don't understand is Turing complete with respect to what? And what I meant is that people were taking hardware, hacking on scripts. Those scripts were only reproducible on that particular instance of hardware. And you get back to the days where you've got ambiguity. So because I wanted a standard module, a standard operation, a standard library that I can reuse, I could start to build this hardware. Now, if I could then make it recursively enumerable, I can suddenly I have programming logic within the programming code. So suddenly I can write loops and conditionals and say, right, if on this, do that, and then when that happens, do that, and have multiple resources and solve the combinatorial graph in real time. So I could basically say have one Chemputer with 4 reactors, 1 separator, 1 evaporator, 1 purifier. And what you do is like, the reaction starts 1 hour. 1 hour later, the second reaction starts. 3rd hour later, 3rd and 4th. Why? Because after 1 hour, the reaction is done. It goes to the separator. Leaves 1 hour to do the separation and do all the other stuff. And when that's done, goes to the next one. And you're sweating the asset. You're able to use all the resources in your... and you have to write software to do that. In fact, you probably know yourself that scheduling software and synchronizing things for job running is actually really important for the utilization of digital and physical robotic resource. And so if we can find a way of scheduling that for making more compounds, the chemists can make more molecules per day than they could ever dream of before.
Yeah, I mean, it's effectively putting the machine into overdrive, utilizing it almost to full capacity. And then secondarily, again, in my own head, I'm thinking, yeah, but if you perfect this, you wrote the software for that, it's reproducible on all the machines. You've effectively open sourced, here's how to make X, or here's the experiment I did. Literally, you can set it up identical. And the paper is almost in code format at that point. Exactly. Very interesting stuff.
Well, one of the things I did before I started the company, and I don't know whether the company likes me for this or not, we'll find out in the end, is with a programming language, I decided I would release the programming language to the entire world. I'm in the middle of doing this right now. And in fact, Schmidt Futures gave me some help, not just money, but just mentorship, and because they try to make me more user-friendly. So stop arguing with the chemist, be nice to them. I'm like, okay, I think it's good to do that. And because you want to actually enable people to adopt the standards in chemistry, it's like any academic discipline, there's lots of competition, people want to be first, people want to do this. But and also the programming language I developed is obvious, right? Like, it's obvious to everybody that needed to happen somehow. So I think that people are beginning to lower the barrier there, and there's no ego in it. Say, wouldn't it be great if we just adopt a common language? You can call it whatever you want. You could insert your surname here, just use the same language, right? Because then people can start to write their own code to make their own molecules and exchange them. So what we've done is we've been able to read the literature. Well, what I did actually, first of all, is I used the summer school, the money I got from various organisations, including Schmidt Futures and in the UK and so on. I had some summer schools where I got students to read the literature and then encode it into the programming language, and then to basically take really popular recipes and encode them. And we've made a series of translations. They're using hybrid models, and we're going to start releasing these KDLs to the world. Probably about 1,000 a week. We have about 40,000 in a database.
Releasing what every week?
About 40,000 chemical codes.
Yeah, I think you said KDL.
Yeah, that's what we call them. So the chemical programs are called KDL. So,
Okay.
And that's the Greek letter Chi, DL, but we just call it XDL because it's like on a normal keyboard you just say XDL, and it stands, so it's chemical description language that runs in a chemical programming language. And so there's a KDL for each transformation. So you should be able to say, oh, I want to make, I don't know, the drug lidocaine.
Right.
And where's the KDL for lidocaine? Oh, great! I just run that on my robot. There's actually a company that makes lidocaine in Denmark, and they came to me and said, "Oh, we saw your paper where you made lidocaine using this KDL. Can we adopt it and use it?" I said, "Fine." And because it's a more rigorous way of expressing, like what it does, it expresses the conditionals. It expresses what reagents you need. You have a way of putting the batches in there, looking at the quality of the materials looking at the process parameters, checking that everything is gone as you expect, checking the hardware is working as you expect, and so on. And the other thing about KDL is really cool, is you basically, a human being could take their lab book, where they've just been writing all their chemistry, scribble, and they think they've written the perfect representation to publish. And what we're going to help them do, and this is the non-profit version, and I think Chemify will also help academia do this because it's in everyone's interest. It's a bit like there's no point in one company trying to own like all the knowledge in any discipline. It's not going to work, right? What companies need to do is add value and sell products and sell services to people. Sure. But there needs to be an underpinning enabler. And that's why I'm kind of in these two roles. And the underpinning enabler here is, if I could take everyone's lab book in the world, convert it into KDL, error check it, say, oh, temperature is missing, pressure is missing, oh, your hazards are missing, this looks like it could blow up. You may want to put something in there, and then from the KDL, that's like a standard representation, human readable. You can then read it back, but not just in English, in French, in German, in Spanish, in Portuguese.
That'd be incredible.
We made one actually that goes from English to Russian, English to Chinese. But given the current geopolitical tensions, I've gone on shelved, and we have to have German in there as well.
So this leads to sort of two sides of my brain thinking of this. One is this is almost like democratizing chemistry as a whole, which would be pretty unbelievable, pretty incredible. But then there's the other side of the brain, which is going, yeah. If you get certain rogue chemists publishing these KDLs for download or whatever, and you can all of a sudden make cyanide or ricin, I don't know, something that you shouldn't. Most people would be. It'd be scary if it was out there. It sounds like this would be also kind of a scary thing on that front. I guess sort of depending. So my mind definitely goes to the two opposites there.
Well, yeah, I've thought about that a lot, and I think there's a quick answer to that. You can already make it. I'm sure there. Well,
that's true.
You can. I don't know if there are any YouTube videos of making ricin. I doubt it. I guess they'll probably take them down. But there's certainly the terrorist handbook out there that everyone used to download, right? Which is kind of I probably shouldn't say that now, but it's like when I was a kid, I was always setting fire and blowing things up. I just saw actually a news report of some poor kid making a improvised explosive with a soda bottle and getting incarcerated for it. I was like, wow, I would have been so in prison. But let's get back. So right now there's nothing stopping anybody going on the internet and finding out how to make stuff, go and make them.
That's true.
Now what we're doing, I think, in the same way, I suppose you can get a drone and attach explosives to it and make some kind of weapon. What I think is really important is to think about why would we automating these things. You don't want to be making recreational drugs necessarily using this technology because it's not going to be pure, and you have a very high chance of doing harm. But what it will do to speed up the chemist in the lab, in the same way that biologists do protein synthesis, and they do gene sequencing and then they do gene engineering. There's potential for great misuse there, but we've got
tremendous potential.
And there's quite a good way of securing that. So I imagine then the current following scenario. Academia can always do dangerous things, right? We're doing chemistry in the lab all the time. It's super dangerous stuff. People could die. You have to take it super seriously. You have to have proper protection, body protection, eye protection, face protection, hand protection, and all that. You work in a fume hood. You hazard assess everything you do. You have to adhere to safety protocols that you learn over many years, and you have training. So that's the first point. So these devices will be in those type of laboratories whereby you are trained. But just think about it. Imagine 20 years' time in one lab, you've got a computer or the equivalent, rather than having, and they're about to try and design a new drug. And to design that new drug, and they think they've got a killer idea that's going to, a saving idea to save a load of people. But normally to make the molecule would take them, 2 years because it just takes too long. Instead, they could use a system to do it automatically, sequence it so the molecule's ready on demand because they have the code, and they could do the biological assay and then make the discovery. So suddenly the positive impact on human health just goes off the charts. So that's one point.
No question there. I mean, even fairly recently, I would imagine if the Chemputer was out and we were able to mass produce, et cetera, I would imagine that would have been pretty great for sort of like the COVID-19 vaccines or all the stuff that we were trying to get as much as possible of in a very short period of time. So no question, that's got tremendous potential.
Actually, our mini robot, the mini one we made, can make RNA.
Really? It can do mRNA?
Yeah, RNA synthesis. So we could actually, I was joking with the team, we could actually make the Moderna vaccine in BaristaBot, as we called it. But we were like, yeah, you probably wouldn't want to take it. It's probably quite impure. I mean, the standards that people go through in these manufacturing facilities is tremendous, right? And nothing is left to chance. I know lots of people like to talk about, questions about what the vaccines do or don't do. But in terms of human health and statistics, we take this very seriously, and I know there's a conspiracy everywhere, but it's just, it's just physics, right? The problem with physics and chemistry is hard to do conspiracies with data. Sure, you do something statistically something happens. When it happens to you, it's a conspiracy. When it happens to a population, it's a population effect. But not going there. Going back to the point, in the future, when we have these machines, let's say a Chemify basically is like the Apple for digital chemistry. Have you tried taking an Apple machine apart? They've got the wrong screwdrivers and all this stuff, and
This is really hard to take apart, actually. I actually haven't tried, but I've seen people. It's brutal.
And not only that, you have tamper machine. You take some iPhones, they've stopped that now because people got stroppy. Because everyone's smashing their phone. Take it out, you get a cheap, and they would say, no, this is not an Apple-approved phone, and it bricks it. Of course, what Chemify is going to be doing is making sure that KDLs are digitally encrypted, and you get user rights management in the KDL file. You probably could even put GPS coordinates, right, or require. So if you don't have a license to run it at that GPS coordinate, you won't run. It just won't. You won't have. So there's a digital rights management in the same way Netflix are turning off people
exactly
sharing the password. So it'll be actually relatively trivial to protect. Right now, we don't want to protect it. We want to make sure all the chemists in the world can basically publish and exchange and talk and build on each other's work. I don't know if I like the word democratization. I think what it is, it's actually just fair exchange, right? Because democratization is kind of like, it's like everyone has a right to do it. No, you do not have a right to make a molecule right now if you're not trained. I'm sorry. I'm not going to be an elitist. I'm not saying you can't do it. I just would like you not to be making those molecules because they could kill you, they could explode, they do stuff. However,
exactly.
But me as a chemist, if someone has published something in the literature and they've had the glory from that, say their Nature publication, say it's on the front cover of Nature or Science or somewhere or Cell or the Lancet, and I want that molecule. And to get that molecule, I have to read a PDF. And the description is not complete, and it takes me a year to work it out. That is absolutely unforgivable. You wouldn't go to GitHub and just say and just pixelate all the stuff and it wouldn't come out, right? Everyone would be on Reddit go, that doesn't work. So my vision for computation for academia, standard programming language, standard description language, people implement it in their own modules in their own way, but adhere to the standard. Then when they publish code that's executable on any device that adheres to that standard. The same way an MP3 is portable on any MP3 players, although they don't exist anymore because I use Spotify. I guess everyone else does, but you know what I mean. So there's maybe USB as a USB plug or something like that, but even then going now, because why would you use USB? Just connect to Wi-Fi.
I think it's moving to USB-C, but I don't know. It just really depends on what everybody's moving
Wi-Fi's
towards.
faster. Yeah. Wi-Fi's just. I was was downloading something onto a USB stick on my main computer and putting it on my laptop, and I was like, why am I doing this? Connect to Wi-Fi, shift, and it was just. And also, most of the USB discs are made in a certain country, and they've all got spyware on the headers anyway, right?
Some of them do. I think the USB is actually pretty fast. It's usually the drive attached to the USB that's pretty slow for the solid state.
Well, I know one of I know the person who makes those actually is a Glaswegian electrical engineer who made a lot of those. Very famous. Is married to his partner's Taiwanese. They now live in Singapore. And,
okay.
And he's like, he was really nice to me. It's called FTDI chip, Future Technologies Devices Inc. And so that I blame him. Your drivers are too slow. But what they did is when people started to rip off their drivers, they made a bricking mechanism, and everyone was complaining that their rip off Android whatever was getting bricked because FTDI was like, please don't steal our IP.
That'll happen. Earlier, you mentioned sort of AI, and we've been talking about the Chemputer, and I think there's definitely a divide in the field right now as to whether or not AI is actually able to help do molecule and drug discovery. But I think you might have a pretty sharp opinion on this one. What does that look like from your perspective?
Okay, I mean, so I think that AI is very good at finding hidden relationships in data, if the context is known. And so what I would say is that drug discovery appears to be right now an act of serendipity, and that means that something outside the known happens. So if you're relying on training on the known, you are not going to absolutely predict something in the unknown. You're not, because you don't have the training data. It's just like AI is not magic. What AI is good at, I would give, is a kind of interpolation. It will allow you to get new combinations of things that are, so you might be able to twist together some molecules. So you might be able to do something, but I'm not convinced. And I think that it's not against AI. I have a very, I'm very suspicious of the way that physics describes reality and the way that computational physicists describe reality with computation. So bear with me. So there's this description of reality that physicists say is this reality. Then, I think it's the first time I've explained it this way, actually. I've only just come to this conclusion the last few days. So physics reality, great. Computational physicists describe that reality in some kind of simulation. Great, so you've got that looks good. Then suddenly you extrapolate up and that you think that basically that computation actually can invent stuff. And what I've been trying to do, and actually you won't see it on here, I'll move the camera, you can see that cube in the background is actually a 3D cube playing Conway's Game of Life. I like Conway's.
I can see that. Yeah, I'm fairly familiar with Conway's Game of Life. That's interesting.
And it's running in 3D. And one of the things I have that on running in the background is I'm hoping that one day it will actually become a proper life form. Like it will start to do things that it's not predictable in a normal length of time that I would expect, it to do the computation. So there is this kind of question that I have. One of my dreams, and I know of the very inspiring computer scientist I know in York, a lady called Susan Stephanie, who I just think she's a total genius. And I remember telling her about I want to make an artificial life form and a conscious, and she's like, I want to too. I want to do it in a computer. And I was like, oh, that's not going to work. You ain't got enough resource. And she kind of said, but look, all I care about is open-endedness. And I want to write a program that basically does things that is so shocking to me that I just never turn it off because it's just so novel. And so one of the misgivings I have about AI is posed now that we are fooling ourselves that it's novel, right? Because ChatGPT is able to just literally make stuff up, which I think is quite good, actually. It elected me to the Royal Society when I did it last time, and it gave me a prize. And I was like, oh, thanks, ChatGPT. I'm not in the Royal Society, and I don't have that prize. But thank you for telling me I had that. That was awesome. And it also made up a few Nature and Science papers I didn't have. And so, now how did it do that? Because you'd argue that's novel. Well, it just took stuff that was in the corpus of knowledge and joined it together rather randomly. Is that new knowledge? And this, for me, is a fundamental question that I'd love people to debate. I would argue it is kind of, if it's new to you, it's new, but it's not new to the entire data set. That matrix multiplication was always going to give that. If you went to ChatGPT and say, please, ChatGPT, tell me this, and you store the random seeds and all the way it runs through, if you recreate those initial conditions with the same training set, nothing changed, you should get the same outcome each time. Okay? The thing is, it has some variation, it has some random numbers in there, or have a way of sampling a model, right? There will be some, unless ChatGPT has some kind of physical random incorporation, and that'd be pretty cool. That'd be mind-blowing if they do that. I don't think so.
I don't think they do physical. I think mostly it's based on transformations.
Yeah.
Or transforms, which is a deep learning mechanism for NLP, as opposed to some of the other ones, which are fairly different.
Great. But so the question is, when ChatGPT does something that looks novel to you, is it really novel? That's an open question. I think it's provably no, but I think many mathematicians would argue. What I would like to do is to make genuine novelty, which is something outside the set that's never ever predictable from the members of the set. And I would argue that ChatGPT is predictable. It's just a very large database where you can keep recombining. And so for me, now if you take that to drug discovery, what does that mean? That means you take the known molecules, known drugs, you encode them, you mix them together in somehow, and sure, you can make new chimeras, and actually you might invent a drug that way, and I might concede the AI has made a drug. But I think it's more likely, because those motifs have been, that if you had a system that could sample members of chemistry way out of the set, and not even in principle generatable from the membership, that you would have a much larger chance of doing something new. And I kind of changed my mind about the hardness of the stance, because I'd like to take hard stances to learn from people, right? I'm a very good... and I was like, I've kind of almost changed my mind that it's in chemistry that you might be able to get some really good candidates out from an AI system, as long, and this is where Chemify comes in, and my lab and the rest of chemistry, as long as you can make them. So if you generate a load of, so let's just say you train, you take known molecules, you encode and you train the transformer model, and then you generate lots of other molecules. If you can't make those molecules, you're back at square one. So my initial dream would be, I have this joke lecture, it's not a joke lecture, it's a real lecture, so we should do Chemputer's dream of electric drugs. And it's like the Blade Runner, like, do androids dream of electric sheep? Are androids really conscious, right? Mm-hmm. So could a computer really come up with novel chemistry that could basically be a drug? And I think yes. And how do you do this? Well, you do it in three ways. First of all, you basically generate, using quantum mechanical methods and your known building blocks, a space of possible molecules. Right. Then you only select from those molecules you know you can make. But in addition to that, you allow yourself to not be target driven, just to follow the reaction, just mix stuff together randomly. You blindfold the robot. And you say, and so it goes, what happened there? What happened there? What happened there? And then you have a chance of finding new molecules and new reactions you didn't know could even be generated. And I think those three approaches together will allow us to make AI drugs work. And it's super exciting. So I've shifted my opinion, because I think there's a lot of smart people doing this thing I think is dumb. And I'm thinking they're really smart. And I'm saying that that's a dumb thing they're doing. I think I'm not understanding what they're doing. So I'm going to their approach, and probably, and I don't mind being dumb if I learn something. So I kind of been poking them just a little bit.
I think we all start dumb until we learn something. So that's not a bad approach to take. You mentioned physicists have a certain model of reality. And something that was sort of weighing on my mind these past couple of weeks since we last spoke was you mentioned that you had a theory around time, the fourth dimension, and the emergent properties thereof. Can we dive in there?
Okay, yeah, that's good. That's good. It's completely crazy, but I don't think it is. Yeah, so the traditional notion of time. So I think that yeah, yeah. I have a really interesting view on time because I actually think I can remember when there was no space for me, and that was and then there was space. There was kind of, I think, a very interesting thing that scarred me for life. Right? I don't know. Um, so. So right now, the traditional view of the universe is we have this three-dimensional universe in space, and we can move in space, right? And so if I've got my two hands, I can move my hand here, I can move my hand here, and move my hand here, do that, can cross over, so they're moving in space. And they can go back, so I can go here, go here. Okay, so in locally, I can go back to the same place. And to move there, I use time, I action in time. And if you talk to physicists, and they say, yeah, time doesn't exist, it's just something you measure. Time tells you about ordering events. It tells you about, you have to, it's just measuring dissipation of energy, things happening. Things happening, you generate time. And for the longest time, forgive the pun, I've always felt that that doesn't feel quite right. And I wasn't able to put a finger on it. And I think this goes back to me trying to understand where life comes from. Now, there is a view of the universe whereby the universe has a beginning, the Big Bang, all this order at the beginning. Big Bang, time, everything goes out, and then there's a big crunch, no universe again. You can just go. And maybe you can even take those points and fold them around and they're the same. So you go that way, you go all the way back in the universe, right? So what it kind of says, if you really do the mathematics and the logic properly, it says, there is no free will. There is no free will. There is no agency. There is no consciousness. There is no anything. Really, it's just stuff is happening. It's Laplacian. So Laplace was this French physicist, I think, who basically thought the universe entirely deterministic. And if you in principle knew the position and momentum of every particle in the universe, you knew what the universe would do forever. Then they said, oh, thank God, quantum mechanics has solved that because quantum mechanics is actually random at the bottom. But it's not. Quantum mechanics isn't random. It has to be, you have to sample things at that size probabilistically. So there is a probability distribution, and it's you have to accumulate statistics. But if you really went down and tugged on the individual atom, the atom's not doing something magical. It's completely controlled by deterministic equations. So, how is a deterministic universe capable of all this novelty? And the other thing that I find interesting is, for me, my experience of the universe is that the universe is continually generating new things I couldn't predict beforehand at all. Although I did make a conjecture for a retreat I'm going on in a few months, that they said, say something non-obvious that you think would happen in 2028. And I was like, Vladimir Putin will be on a witness protection program in the US. Let's see if it comes true. I don't know what the sequence of events it would take. I think for that
Interesting. It's an interesting prediction.
Well, look, let's imagine the reason I said that, it says that everyone sees that Vladimir Putin is a bad guy and he's doing bad stuff. Sure, but he's not a single individual. There's lots of individuals going. So why is he doing what is he doing? There must be a series of pressures. People don't just act alone. So then, if actually Vlad says, oh my God, I don't want to be doing this, I'm being forced by this other set of environmental circumstances, I don't want to be at war with Ukraine, I'm going to actually tell you what's going on. And they basically, then, I don't know, I'm just like thinking, are individual people doing stuff? I digress. Time. So I think that, so I'll cut to the chase. I think time is the only thing that exists and there is no space. And people were like, this is just insane. Well, hear me out. I move my hands, in space, but are they in the same space? Think about it. I'm on planet Earth going spinning. I'm going around the sun. The sun is the solar system is moving through space, through the universe. So this is actually physically new space right here. In front of me is new space. That's space with respect to the rest of the universe. I'm traveling through a new part of the universe. I never go back to the old part of the universe. I have local reversibility. I go back. And so what we can say is that every event is unique in space and time. But if you only think about time as being a thing, then space doesn't really need to be a thing. Sorry, you're going to say something.
Oh, I think we were talking about sort of the local relativity. Just so for people who are listening, it's effectively, given that we're hurtling through space on this blue marble, the blue marble is being whipped around by the Milky Way, and then on top of that, the Milky Way is actually expanding itself outwards. Every moment is effectively brand new space, but locally it appears to be the same space, even though it's not. Is that about right? Okay.
Yeah. So space is not reversible. And the physicist's model is locally reversible. But the problem is that so I do agree the measurement of time could be deemed to be emergent. But I'm saying there's another fabric below space that we call time. And what that is kind of like, think about it like a chessboard that's expanding into the infinity of states. And that's just this novelty space. The basically there is this series, this kind of imaginary physical matrix of boxes where there are continually for existence more boxes are being generated, and when you happen to move between those boxes, you do a measurement, and that's what you call emergent time. But actually, if the boxes weren't being generated by this mechanism that produces a universe, you wouldn't even be able to measure time between them. So why am I saying all this nonsense, right? I'm not qualified to say this, right? I'm a chemist who's pretty bad at chemistry, as I've just explained. I'm not a particularly good engineer. I'm a pretty bad programmer, and I'm talking to you with authority about time. Insane. Well, yeah, but I want to understand the base of the universe, and I want to understand how novelty comes in, because novelty somehow gets invented by the universe and gives origin of life. But if you go back to the origin of the universe, you have this problem where we just don't understand where the arrow of time right now is a statistical arrow. We observe that if you put some cup of hot water, it will cool down. It's just statistics. It bumps into things, and what the physicists say is like, look, at the beginning of the universe, it was all this energy and all this really low order, and ever since the universe has been unwinding that, and we're going to dissipate into a heat death. And I don't think that's correct. I think the reason why this is, you need four things. You need to have origin at the origin of the Big Bang. Where was the little, origin thing you put in? You need to have order at the Big Bang. So where was the ordering machine putting all the order? Then after the Big Bang happens, you have to have the second law. So this is asymmetry in time, which may be best represented by the fact that you then have this kind of statistical kind of observation of, if you have order at the Big Bang, the second law kind of comes out. And then thirdly from that, you have time, and then from there you have causation. So time and causation actually come out at the top. And so now if I act on myself, if I'm a macro state, and I actually, were able to go to the lab and make a drug at atomic scale and take that drug, maybe you shouldn't, it's a bad way to look at it, I'm not Heisenberg or anything, but if I'm able to do something to myself at the microscopic level, on the macroscopic level, that kind of breaks some kind of conservation, right? Physicists and philosophers don't really understand this top-down causation. So they're coming up with all these things, emergence and all this, and I think the simplest thing is to say, we never see time frozen. So what I think people might agree with. So, and I know that, people like Eric Weinstein just kind of like to say, nonsensical things because they're outside of academia and they're heretics and we ignore them. No, we ignore them because they're genuinely just making stupid statements. Okay? Like
they're entertaining though.
Yeah, but that's fine. But pretending to do it with authority is not fine. And then pretending to kind of go onto the zeitgeist and then have these arguments, that really makes me angry, because really everyone then is a conspiracy theorist. And I don't know, maybe I'm way out of my depth on this, but what I was saying is that speed of light seems like it's constant, great, because that's the speed of causation in the universe. So so that's one important thing. And the other thing that we can see is that you can't go back in time. Everything has to go forward. Every measurement you make, everything you do, it's not, this reversibility is borrowed. And so I think that because you can't freeze time and you can't go back in time, and physical processes occurring all the time, that there's a lot of evidence, I think, if you shift your viewpoint, to argue that time is fundamental and from time comes everything else. But it's a fun thing. At the end of the day, it's a crazy conjecture, but it's not any crazier than the current construct of the universe. It doesn't violate. I'm not saying that you could go faster than light. Absolutely not. So you can't. There's no reason for that. I'm just saying that basically you don't need order at the beginning of the universe. But here's a wacky thing, right? So I think space is not space, it's time. It's like, what are you talking about? It's like, take the Voyager probes. They're so far away. They're far away in space. Sure, we can measure them far away, but they're actually just far away in time. We had a limited amount of energy. We fired them out there. They've gone away, but we could catch up to them if we could, if we had enough energy. So that's really interesting that time has really stretched them away. And if you imagine, if you drive down a highway and you imagine that highway, the highway, you're going in a spatial dimension, but you're driving down, it takes time. It took time to build that highway in the past. That highway will not exist in the future when it erodes away. That highway is a temporally defined object. And so I wonder if the universe, having this size in space, is an illusion, and it's really just got size in time. And so time only has meaning when you can see effect, cause and effect. So I'm wondering if the universe goes around something along the lines of, you have this Big Bang, everything interacts, there's a lot of interesting stuff happening, stars, galaxies, planets, consciousness, GPT, TikTok, and then the universe expands, and then when all the particles in the universe are so spread out, they lose synchronicity, then space fails to have any meaning, and you find yourself back at the beginning.
Which begs the question, of course, if everything is deterministic, that means you didn't really have a choice but to do this podcast. You're sort of destined from some type of beginning of the universe.
Yeah, so the initial conditions describe what we do. Yeah, I mean, it's completely nonsensical. It can't be the case. Now, well, why is that? We have to do experiments. So I was going to say, right, I can come out with a lot of these outrageous statements, but really, they're just outrageous statements if they're not falsifiable. And so, and that's one of the things I like to do. And I can falsify some things. I'm not sure how easy it is to falsify things about time, but I think we might be able to do things with causation and understand how life got started by generating kind of causal structures, making complex molecules, making memories and substrates. Those memories allow the universe to then turn into an evolutionary system, and that evolutionary system acts on itself in some non-trivial way. But I would really love to just do one thing in my life, if I can do anything, that is build a machine that will generate novelty, where you put boring in and you get novel out, the novelty bot. And I still haven't yet. It's like kind of almost like the paradox that there is in incompleteness theorems and in computation and in evolution and in quantum mechanics, whereby humans can kind of imagine proofs and things, but they kind of seem beyond the current event horizon. And I wonder if our ability to imagine things that don't exist yet actually help us construct things into existence. So there's this very weird thing that humans can do that I just don't understand. And it might be that I just spent the last 10 minutes talking complete gibberish, and from that I'm potentially sorry, but there might be an experiment in there somewhere where we can measure And then we might actually get to grips with what dark energy and dark matter are from rethinking this, because all is not well. Gravity and quantum mechanics aren't playing well together. So that says something's wrong. There's extra mass in the universe. That says something.
Every single time someone says dark matter to me, I always say, why don't you just use the word MacGuffin?
Well,
they're describing something that we can't measure, we can't see, we just think exists because our math basically isn't strong enough to prove otherwise. So it's literally like the ultimate physics MacGuffin.
So I think that dark matter might have, So I think there is all they're calling this thing because 96%. If you're gonna, I'm probably gonna say this wrong, but roughly I think 96% of the mass in the universe is unaccounted for, something like that.
I think I've heard that, somewhere around there.
A large amount. And the reason why it's unaccounted for, because on the large scales, we don't understand the gravitational structures. And cosmologists have been building pretty convincing computer models. And while I'm saying at the same time, you can't predict the future precisely with novelty, on cosmological scales, you can predict some features and also predict how gravities will form and black holes and all that. So, but yeah, I think there's more evidence for dark matter than there is dark energy. But even so, it might be that this dark matter is this thing that doesn't interact with anything that we know of yet, and that it might be something that is associated with the fabric of space, if space exists. But yeah. We need more observations, and I think we need to basically be able to get to grips with those experiments in lab. But if these MacGuffins don't interact with anything that we know, they only interact with other MacGuffins, then it's like MacGuffins all the way down.
As far as this theory, right? Meaning time being the fourth dimension. Let's just assume that it's true.
Mm-hmm.
Then what? What does that mean for humanity? Or what would it mean?
Well, I think what I would like to propose is that time is the fundamental thing from which space emerges. I'm not saying that space doesn't exist at all. I know I can go to my lab in space and come back, but it's kind of interesting that I'm not going to the same lab. If there's all these layers of space, you have all these concentric circles going out, it's going in a different place. So what I think it means is that there's no going back, right? So you get rid of all these paradoxes, no going back in time. And also what it means is that when the universe is expanding in time, and this seems to be the mechanism there's some way that we can interact with that mechanism to generate novelty in the universe, new objects. So every time, computationists and physicists would argue that there is nothing ever new, that you could always predict something is new from what's gone before. Here's an interesting thing. You've got this known universe, or the set of known things. Whenever something exists outside the universe over here, or comes into being, that you didn't predict from in here, you can always encapsulate it you expand your knowledge, because it doesn't break the laws. It's consistent with it. But there's always this event horizon and new things happening. Who would predict, that whatever meteorological event or whatever this, and everyone would say, well, it's, lack of understanding of initial conditions, all that. But is it? Is it because the universe has more states available to generate things, and it's scaffolding on stuff that's happened before? The universe is intrinsically open-ended. And so I guess I would like to come up with a conception of that would allow me to do a test where I almost could have two different mini universes, if you like, or two different experiments where I could generate novelty at different rates and see systems that had ostensibly the same initial conditions, but as I manipulate them, one is more unpredictable than the other. And that would be kind of cool. So I can imagine experiments like that. But what it would say for humanity, I guess it would say that, the future's open. Genuinely. It's the way the universe is deterministic but undeterminable, which is kind of nice. So that means that the universe does behave relatively uniformly. It is deterministic. But because the universe is expanding in time, you literally have to have a breakdown of... There must be some breakdown of causality at some level, because because you don't have all the mappings. So that's maybe why. So I'm really interested in breakdown of causality. That's, I think, how we can measure it. Mm-hmm. So, and if that might help us understand origin of life, intelligence, consciousness, and kind of, an evolution. And they all seem to be related to this same novelty generation problem, or what I would call, very simply, open-endedness. By biology starting on Earth, it started the sequence of events that connected the very first cell with ChatGPT today. Why? Because if it wasn't for that first cell becoming, going through evolution and then basically undergoing a transition to animals in the sea, and then to mammals, and then all the way up, and then human beings and mathematicians and so on, that lineage in time is what, when you see ChatGPT. So when someone says to me, oh my God, the cell is so complicated, how can you justify it? What do you see when you see the cell? I say, I see 4 billion years of an object. And objects extend through time, and time is just another dimension for objects, because, you have parents, grandparents, all the way back, right, to, our last universal common ancestors there. So I think that's something that humans, scientists, philosophers forget. They think that they're the only instance. But if it wasn't for their history and the history of their cultural artifacts and technology, they would not exist. And that's really interesting.
Makes sense. Speaking of those sort of humans and whatnot, and going back in time, intelligence was invented by selection. Mm-hmm. And therefore, there won't be any super intelligence without super selection. I believe this is a direct quote. Help me out on this one. What are we talking about when we say this?
I think there are people out there trying to crack intelligence, and I think that what they mean is they're trying to understand enough about how intelligence works to use it in a modular way to solve other problems. And I might even buy we could do that, but I don't think we really will be able to get sentience. I think if you think about the brain again has gone through this linear evolution. So you've done 4 billion years of evolution, then the first brains were evolved, trial and error. So your brain isn't just your brain now. It is the lineage of all the brains that have existed. Whoa, that's a big depth in time. And it's a function of the fact that your brain grew in the womb and then during childhood. Great, so you've got all that stuff. I don't know whether you're a fast myelinator as a teenager, or ask you about how crazy you were or not, later. And then and then you're
teenager crazy. I got boring later.
Right. I was boring. No, I'm making up for it. And then your brain works in real time. So you've got all these different things that your brain has been doing. Now, if you want to invent intelligence, do you need to create 4 billion years of evolution and in selection? Because selection, you survived. Your brain survived. How many deaths have there been so you could survive? Both how many bacteria have died so you could survive, right? In the trial and error. At every level, death is the default. It's a struggle to be alive. And survival through selection creates, innovates things. Your survival has been due to something in the environment. So when you go from the transition to single cell to multicellular systems, and then onward, selection has got supercharged. And now, if you think about the way that we're using, let's go all the way to mammals. So suddenly we get to mammals, and we start to make tools, and we start to maybe be able to produce language. And when we came to Neanderthals, Homo sapiens, and whatnot, our thumbs become the right size, so we can make tools and then basically encode things. And now we start to bootstrap. So the first tool makers were like, wow, I have an advantage over you. I can use this tool to live longer, get more food, defend myself. And what selection allows you to do is invent tools, invent language, invent abstraction, and literally the invention of consciousness, if you like. Conscious thought is through selection. And when you're making decisions down the street, when you're basically working out who to talk to, what to go buy, it's all a selection experiment, right? You think you have autonomy, but selection is in control. And there is a way we can rise above it because we build abstract machines. But I'm just wondering if the architecture of our intelligence has been produced by selection, and until we understand that, we ain't going to get any superintelligence. I mean, I think it's nonsensical. Like, oh, we're going to build a superintelligence that understands things about the universe that we don't know. Really? Okay, give me an example. And it's just like people generating nonsense above a horizon. It's like it's going to be able to solve mathematical, conjectures fast. It's like, well, yeah, but that's a combinatorial search. It's going to do that. You built it. It's a bit like saying, oh my God, with a super test tube, we're going to do super chemistry. It's like, it's a test tube. So when people say to me, is AI going to get a Nobel Prize? I'm like, no, the person who invented the AI will get the Nobel Prize. You don't give the chemist who used a test tube to get a Nobel Prize for discovering a new drug, the test tube, the Nobel Prize. So people don't understand bootstrapping. And so what I'm saying about intelligence, which I think is very nuanced and maybe a lot more mainstream and somewhat boring, is to say that the tools we have are not intelligent on their own. When we interact with them, we get them to be intelligent. The question is, can these tools be intelligent on their own? No chance. There is no prospect. Have you tried? Although I can't wait to get Bard. Is it Bard or whatever?
You're talking about Google's new AI?
Yeah. So I've been getting these chatbots to just talk to each other. I think in the end, the internet will just explode and be non-usable within about 10 years.
You mean the chatbots basically going to war with one another for some definition, just nonstop chatting? Yeah, I think that's happened. It's interesting. Facebook actually did that a long time ago. They had two chatbots that they got to talk to each other, and it turned out they thought there were emergent properties, and they thought, oh my God, they're inventing their new language, and it turns out it was just bugs. It was just bugs in the code that they eventually degenerated into no longer speaking English. But yeah.
Yeah, I heard that.
Chat GPT is interesting for a number of different reasons, but yeah, that versus Bard, and then I think the Chinese have invented or are working on one for Baidu as well. I think it's everybody's going after this sort of new technology.
But it's going to be a bit like, I don't know if you've ever done this for fun. You take a YouTube video, download it, and re-upload it, download it, re-upload it, download it. Because it's the way the compression works, so you only need to do it 10 or 20 times before it's just noise. And so I think that we really don't understand the causal structures that give us intelligence. We really don't understand this kind of the scaling, right? I can give you, and everyone, all computer scientists hate this. It's like every time I say it at any public forum, they take me on task. But I would say the following statement: that there are more possible connections your brain could make by reorganizing the neurons and the connections in your head than there are atoms in the universe. So there's that what that means, you can't access them all at once, but because you can shift around plastically, you can basically, you've got all these configurations, you've got all this state space available. On a microprocessor, it's always going to be a compressed version. So these large models are always going to be compressed representations of reality. They're not reality. This is the same reason why the simulation hypothesis is not a hypothesis. It's just nonsense. And the reason why it's nonsense...
Yeah, say more about that one.
So the reason why the simulation hypothesis is nonsense is that you, first of all, if you're in a simulation, you're going to be existing in another simulation, another simulation, another simulation. And what Nick Bostrom does, he says, well, I'm going to assign the probability that we're a normal person here, and I'm going to do all these probabilities, conditionals, and boom, we're all in simulations. No, there could be one confounder there that actually it's not possible to make a simulation that could represent a human being. Now, here's the thing, and this is where selection got there before us. Let's just imagine the following. If, and again, there is a get out clause in here. Again, it's incompleteness theorems for simulations and mathematics may be simpler. So let's just say that basically biology is pretty efficient and all the computational capability in my brain down to the tens of molecules is being utilized. And then, you've got DNA in the cells and all this stuff. So basically, if you want to replicate all of that faithfully, right, not just statistically, make an average, the computer needs to be the size, at least the size of the available universe. And that's with no time. And as soon as time inflates, the computer needs to get bigger. So the fact we cannot predict the future is probably a very interesting piece of evidence that we can't possibly in a simulation. Because when we go right down to the bottom, if causation is really holding, the infrastructure required to simulate the infrastructure we see is always bigger. So if the thing is always bigger, you're never going to do it.
I never thought about it in that particular way. That's an interesting way of putting it.
Now, someone might say, well, no, you're in a simulation, and really there's like this stuff below atoms, and, as the Planck and all this. I'm like, okay, you can always invoke the simulation in the simulation. But, and there may be a really good philosopher, well, I mean, maybe Nick Bostrom is a really good philosopher, and he can tell me why my argument is flawed. But, I was always inspired when I wanted to make a computer. So I'm making chemical computers in my lab for fun. I think the only way to AGI and any real time scale is to just make a facsimile of a brain, make a brain gel. I don't think consciousness outside of silicon, outside of a human brain is impossible. I just think you need to bear in mind the lineage going back to Luca, and somehow you've got to fall that and jumpstart, and you've got to have the configurability of human brain, because that's what has consciousness now. Let's start there, right? And then when people say, things might be conscious, well, a large language model that's trained over many GPUs, over many hours, many days, using many megawatts of energy, that object, when it's instantiated, is that a conscious entity? No, because consciousness needs to integrate information in real time from one side of its compute to the other, whereas these models are like infrastructures built over time. And I'm really just describing that super badly, but coming back to the computation, ages ago I wanted to make a simulation of mayonnaise. And so I thought, well, I'll make a simulation. So mayonnaise is a really interesting material. You've got all this food and these emulsions, and you whip it up, and you get this lovely white pattern that is your mayonnaise. And you could simulate it using a good physics engine. And the physics engine, you could never quite go the symmetry. You can't get the quite consistency. It doesn't faithfully reproduce it. You have to put in lots of information. And I thought, rather than spend all my energy with my GPUs burning all these megawatts, why don't I take the ingredients for a mayonnaise, put them in a jar, put a very fast video camera next to it, and whir the blades so I can make the mayonnaise and actually video it using fast video and watch it. And I wonder if that's a physical computation. And I'm like, oh, that's kind of cool, because I'm actually physically watching. I can then use the high-speed video to work out what's going to happen next. I can maybe do it at different scales and get some idea. And therefore, I don't need to do the compute in the GPU and invert some matrices. I actually just watch it happen. And I think that's a super interesting idea, because what that then does, you can then start to do what's called embodied computation. And embodied computation is what I think we are not using enough of in our current revolution. And so it's like literally doing compute with stuff. And so that's kind of a very long answer to the simulation argument, which I don't think is satisfactory to some people, because I think Nick Bostrom had 3 criteria. But I think one of the what I said is whether you're in a simulation or not, I think he missed the Zeroff one, which is it's just not possible to make a simulation. And if you are a simulation, what substrate are you on? Where are you? Is it simulations all the way down? And then is the universe computational at the bottom? And I think one of the things I want to do with an experiment is I want to prove, and I don't even know how to do this, that the universe suffers from computational irreducibility. Now, this is not exactly the same thing that Stephen Wolfram talks about, but it is similar. And I'm working on some experiments for that.
What's the high level there? I mean, you don't have to go through the whole theory. I'm just kind of curious. What's the high level on between your definition versus Wolfram's?
And mine is much more physically based. I'm not basing it in a kind of that there's compute all the way down, and there are just some things have solutions, some things don't. What I'm saying is the universe is not computational; it's physical, And from the universe, you can emerge computation. And some of the universe, you can do computation irreversibly. Where reversible computation allows you to make Turing machines, right? You can do super interesting things. You can imagine going back in time. You can imagine the simulation. You can imagine the metaverse. But it's kind of it's all about substrate and the substrate dependency. And I think that's very analogous to lineages in time. And so in the same way, you need to basically layer things in substrates. If you take a cellular automata, the cellular automata just isn't kind of occurring on its own. It's occurring in a computer substrate. And, you can erase the squares effortlessly just by basically just turning everything off, and you can then start it again. But that is not a faithful representation of reality and the infrastructure required to make that. That is something that you are able to simulate rather, in a silicon substrate.
Okay. Well, given that we've gone to the universe models, given we've gone through some universe models, what about aliens? I know you've got a couple of theories around this, and I know that there's something called assembly theory, which I think does relate to sort of extraterrestrial life. At least in the physics world, there's assembly theory in computer science as well. I think it's in mathematics. There's a number of different things, but I believe you have a very particular thought on this, and I'd love to hear. Are there aliens? Are they here? What's going on?
Are there aliens here? Yeah, according to I don't. Life on Earth seems to be very special, doesn't it? We don't really see evidence of life anywhere else right now. And so that puzzled me a bit. And so, given that the chemistry that is in life isn't that special, it is special insofar as it's contingent, right? So it's like dependent on the path it got there. But there are no special atoms. There's no, magic. There's no vitalism. It's just chemical reactions, well constrained. It's basically life on Earth is a result of a 4 billion year curated chemistry experiment. All right, so like 4 billion years of curation in chemistry gives you biology. It's amazing. And actually, it was less than that. It was only maybe 100 million years. We don't know. And assembly theory was a theory that I built, a mathematical theory that I built with many. I don't know. Ask me on a different day. I'll give you a different story about how it came about. But it's kind of always troubled me, actually, that I had this kind of description of the universe in my head, and some days I kind of saw it very clearly, and other days it was just like I have no idea what I'm talking about, and it would go away. But now it's pretty clear what it is, and the way I got there was to ask a question, and again I just got in trouble with the chemist, to say, what is the largest molecule that I could imagine that could be made naturally, whatever that is, without information, maybe, without intervention, maybe with no life, if I could even imagine that. Could it be possible to make, wildly outrageous molecules without life? And my intuition was like, no, it's not possible. And when I started talking to people about this, they just said, no, you can do that. You're talking rubbish. Of course, you just do combinatorial chemistry. Molecules get bigger and bigger and bigger. It's natural processes. And then I realized for many years I was describing what I meant. It's like, well, I didn't just mean making a very complex molecule, just one inertia. I mean in a detectable amount, because I'm a chemist. If I can't detect it, if I can't do an experiment, it doesn't exist. To detect a molecule, you need to have thousands, millions, trillions of copies. So I was really not communicating correctly. So my conjecture is really, are there any molecules that you can make trillions of copies out there that aren't made by biology? And the answer appears to be no. And I was like, whoa, that blew my mind. So I started to play with the theory and say, okay, can I even tell if a molecule's complicated or not? And I started to think about this, and I went to the computationalists, and they said, oh yes, we can use all this information theory and entropy and blah, 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 and we'll just count it, and we'll look how compressible it is, and we'll look at these statistics. And I was like, this doesn't seem very right. And they were like, and it's kind of like this. Let's say I ring you up and I say, okay, hey, I've made 2 new drugs. and you're like, okay, tell me, what are they? You know, let's say you're working molecular biology and you want to test them. And I say, right, well, what I'll do is I'll just tell you how to draw them. And you say, right, and I give you the coordinates for one molecule, and say I have to give you 25 coordinates. You write it down. You're like, and I give you the next molecule, and I have to give you 50 coordinates. And you're like, and I say to you, okay, which molecule is the most complicated? And you're going to go, the one with 50 coordinates. Right? That seems fair. And they say, and you're like, well, Lee, look, I don't care about the coordinates. How do I make them? And I say, okay, now I give you the same, and let's say I can make both molecules from the same selection of starting materials, but the 50 coordinate molecule I can make in 2 steps, just by mixing together the chemicals in 2 steps. And the 25 coordinate molecule I have to do 6 steps. Which is the most complicated molecule now?
Bit of a paradox there.
The molecule that practically speaking, it's the one that needs 6 steps, because the coordinates go through your eyes, they're Cartesian, you draw them down. In terms of practical steps, it's like cooking. So then I suddenly realized, information theory is only good for information theorists who are trying to categorize things on a equal footing. But if the molecule is being made in a random gamush in a volcano or smoke, maybe something else is going on. So I kept playing with this, and I realized if I take a molecule, a big molecule, how do I know it's evidence of life or not? Well, what I did is I imagined just cutting the molecule up randomly, and then putting the parts together in some kind of order and ordering them. And the way I do it is like if you take like the word abracadabra or banana, they have recurring motifs. So what you do is you take abracadabra, just cut in the bits, order the bits, and you can go from abracadabra, and the abra is already been produced at the beginning, so you can use it again with no extra information. So what that means is like you're able to take that word and compress it down, and you do that with some molecules. So what I basically would say is like, okay, what am I saying in very simple terms? Take a molecule, break it apart. The more steps it's required to put that molecule together, okay, maximizing reuse. So you could basically use bits again to compress it, if you like, to take the shortest route. Tells me something about how complex it is, and that's how assembly theory started, right? It was a mathematical formalism.
So how do we translate this to aliens?
Well, I'm getting there. It's a long way, right?
Okay.
What you wanted to do is the reason for look for aliens, right? So the way people look for aliens right now, the way that NASA looks for aliens is to look for evidence of biology on Mars or in Enceladus, right? So you want to look for proteins, DNA, amino acids. But what if the alien used a different chemistry? What if the life is different?
Silicon-based.
Exactly, anything, just crazy stuff. And you wouldn't know. So what I wanted to do is to say, actually, is complexity, assembly complexity, the universal alien detection signature? Because I could basically ask, is this object complex enough? I wouldn't need to go with any assumptions about its chemistry or technology. So what assembly theory is the ultimate alien detector, because all it does, it says, I don't care, it's our agnostic molecule detector. I don't care where you come from, molecule. I just want to know how many unique parts do you have. And if you have more than a threshold, the more you have, and the more of you I can detect, the more likely it is that you've been produced by some evolutionary selection or technological process. And that is kind of how assembly theory was born, to go and look for alien life. Now, in the solar system, we can look for alien life using a thing called a mass spectrometer, which basically allows you to cut the molecule up and weigh the molecule. And what we also found, that the weight of the molecule is very good signature for whether it's made by life. So I think the first question is, has this molecule been made by life? Yes or no? Can you do that? Yes, we can do that. Great. Right. Is this molecule is it an alien life? Well, on Earth, you're like, well, I don't know, there's lots of life everywhere. So the further away you go from Earth, if you detect alien life on Mars, you'd be like, wow, I've got life on Mars. That's first step. Now, is the life the same as Earth life? That's the second step. Then you can then determine if it's alien or not. But I would say rather than looking for aliens, you should look for life first.
Is there not a philosophical question inside of there to the point where it's like, well, let's just say, okay, it's not like human life in the sense of it's not even carbon based. How would you know to classify it as life at that point?
Just by the number of parts in it. That's the beautiful thing. We just say, okay, we completely don't care about what you are, stuff-wise. All we care about is, are you so complex that you couldn't have formed by chance? Because if you think about it, if you say you take a coin and you flick your coin and you get heads, you're like, okay, cool. And you flick it again, you get heads, you're like, oh, that's cool, lucky. And you keep going. How many times do you flick that coin to get heads each time before you go, this coin is there's a cheat, there's someone that's actually rigged this, right? This coin is weighted. Maybe 10, maybe 20, maybe 30. If you're it depends on your standards, right? So
I mean, every time you flip it, the chances are still 50-50 regardless of what happened before. But you're right. At a certain point, you're going, this is ridiculous.
That's exactly right. That's exactly right. As long as the coin isn't weighted, so it's not, 99, 0.001, it's 50-50. So if you keep a tally, you're absolutely agnostic each time. You're like, I've got a coin, I know it's probably worked, boom. Okay, heads again. And you might be in a stream of good luck of getting heads in a row, and then when you get to your 20th one, you get heads, tails, heads, tails, heads, tails. So what you need to do is you need to accumulate enough data in population, and that's really a nice way of looking. So what assembly theory allows you to do is to determine if an object has been created by selection or not. And then we started to think about it not just as a diagnostic tool to measure aliveness. We started to realize that assembly theory tells us about causation at the bottom and how causation emerges from interactions all the way up to create objects, and how those objects interact with each other. And I'm working with a team at ASU led by Sarah Walker and with her team, and also some people at SFI as well as in Glasgow. And we're beginning to realize that assembly theory appears to tell us about order, complexity and propagation of causation or dependency on the past. It tells us about how to quantify initial conditions and understand that. So that means that assembly is actually superior to entropy, because entropy only tells you what you lost and you have to label it. Where assembly, you don't have to label things because you can see when you count disorder, you know that that's produced in time. And this is what got me crazy about time, is I realized that highly assembled objects, the higher the assembly index, the more time was required to make that object in the first place. And that's how it's become a theory of physics of aliens and kind of thinking about time. And given that I'm not a physicist, I don't know anything about time, and we haven't found any aliens, it could be a really, really, really poor theory. But there's a really interesting thing, which is kind of cool, in that I've got this abstract theory, a number of parts. I was able to go to the lab and measure the assembly indexes of all the molecules in the lab using what in chemistry spectroscopic techniques, a way of counting the parts of the molecule. And we get a very good correlation. So I'm like, oh my God, I'm talking crazy stuff about this theory, but actually it's measurable. Molecules have an intrinsic complexity you can only measure using assembly theory or assembly theoretic approaches. And it's there. It's like measuring the force of gravity between two objects. So is measuring the assembly like measuring the amount of selection it's undergone in time? Yeah. And that's why I'm like, my brain is short-circuited because I don't know what to do with that right now.
That's fair. Assembly theory and even science aside, you think aliens have ever been here? For some definition of alien?
I don't know. I think it's I don't know. I mean, I do not believe in aliens. I've seen no evidence. So if I'm being honest, I mean, it's like, I felt like saying, just for fun, see how many extra Twitter followers I could get by saying, yeah, aliens definitely exist, right? Because, but I haven't seen any evidence at all that suggests that aliens have been here. Now,
sort of leads us into the Fermi paradox of, if they are, why haven't we seen them? or is it just too far away? There's a number of different things inside of there, but yeah.
Well, yeah, but I'll come back to another thing, and I don't know yet. So I actually started to map all life on Earth using assembly theory, which is kind of cool because that means we don't just use standard taxonomy or gene sequencing. We can use assembly theory to map the tree of life. We might. It's not unheard because we haven't looked for life yet, right? So the only way you can find life on Earth is use your eyes and a microscope. Does it grow? Kill it and so on. Can you sequence it? Can you draw it? Now, there might be other molecules, other versions of life out there we just can't interact with. I'm not saying hyperdimensional aliens, but there might be. It's conceivable, but not likely, I would guess, if I was going to bet on it. But let's say it's conceivable. There are alien microbes on Earth, or microbes on Earth that we have never seen before because we can't gene sequence them, we can't be in the Earth's crust. And could it be that, I don't know, Earth was formed from the death of another star and other planets, and they could have been alive beforehand, and some of that life is in the Earth's crust somewhere, and we could detect it and find it? Maybe. I don't know.
Or maybe that's the reason that the two amino acids decided to form a protein X billion or 100 million or whatever it was years ago when life actually evolved.
I think that having life dependent on life gets you into this crazy book which I've got here, which is this crazy book which I found in Paris in a bookshop, which is like The Intelligent Universe by Fred Hoyle, and Fred Hoyle is basically an alien microbe creationist. And Fred Hoyle almost got the Nobel Prize for physics, right? He was a brilliant physicist, but basically hated the Big Bang and just thought that life was here everywhere, and there are microbes everywhere in the universe, and we see no evidence for that. So to answer your question concretely, I have seen no evidence for it. But however, before I started to think about assembly theory, I'd seen no evidence for complex, often hadn't worked out how to think about it. So I think there are three answers to your question. I haven't seen any evidence for aliens on Earth, but I've now got a way to go look for them. Well, that's super cool, right? We can go look. And what the Fermi paradox I don't think, it's just basically because Fermi had a limited imagination when it came to chemistry and complexity. And Fermi assumed that basically, rather egocentrically, that aliens would be broadcasting radio waves and doing all sorts of random stuff that we would detect. And if assembly theory is right, the way that we are so contingent on our past, aliens might not even know what prime numbers are. Our prime numbers. One of the things I'd love to do, right, if I can actually ever take a day off, I want to find a physical process that gives me primes. Wouldn't that be cool if there was some physical process that just gave you prime numbers?
Be impressive.
I'm not sure I don't think there is any physical process that gives us primes. Primes are evidence of abstraction, and I would probably hazard a guess that probably aliens have got primes. They might not have got all the type of mathematics. They would have mathematics that's kind of consistent with ours, but not the same. And so I think the mathematics is invented, and because we all share the same universe, right? We are all part of the same origin story. We have some overlap in what we call our assembly space, and therefore mathematics at the very core would share some origins. But I don't think mathematics all exists. It is continuously being created by process in time. So what I hope to do in the next few years with assembly theory is basically map Earth and space and the other planets in the solar system using mass spectrometry to see if we can find evidence of alien microbes. But what we can now do is, because we use mass spec, so mass spec is about weighing molecules. We can also use infrared, and infrared is like, looking at heat signatures. But what we've found is the correlation we get with mass spec, we also get an even better correlation for infrared. What does that mean? When you take a molecule and you shake it with some energy, it absorbs in very specific ways, a bit like if you went to piano and you typed a bit of chord, you'd get a particular sound out. So molecules are like pianos. If you hit them with a particular wavelength of energy, you'll get a particular wavelength back, right? Characteristic of the bond. Or actually, more correctly, if you blast it with a load of broad-span energy, it will absorb certain unique frequencies because you're playing the piano keys of the molecule. So, if we can make a telescope the size of the sun, right, then, which should be possible, basically use gravitational lensing and just basically bung a detector quite far away from Earth. You're probably more likely to do it with the Earth or something, or make just a big array. But we should be able to, at some point, image exoplanets and look for complex molecules in the infrared. And we might be able to remotely detect alien life using a really big telescope that will just detect molecules that have enough complexity. And one of the things I want to design before I die is an emergency switch. Like, I want to design a gas. No one's going to let me do this, right? It's insane. But I want to design a gas that has so many different bonds in it that if the civilization's about to end, we want to just pull this and put the gas in the atmosphere to say to the aliens, we were here. Because they'll be like, holy shit, why are you absorbing in all this? Like, I want to basically write prime numbers into a gas, which I think I know how to do. Which should be super cool.
That'd be pretty incredible. A good signature, almost like carving something in a post saying that you were there.
Yeah.
It'd be impressive. So, last question. If you could manifest a technology into existence, I think I might know your answer. You might have already mentioned this, but if you could manifest a technology into existence in your field, what would that be?
Into my field?
Is it the novelty? Is it the novelty generator, or is it?
Yeah. I mean,
and again, for some definition of your field, your call.
Can I have three?
Fire away.
All right, number one, I'd like the Chemputer to be, I'd like to all the hard work be done and just be in every lab in the world right now and just people running code. But I think that will happen within a few years. We've got 50 in the lab, 50, and Chemify is going to be generating a load. I built the Chemputer to build an origin of life machine. And the origin of life machine is a big grid that I'm going to go searching. So the next technology I need, and I've already built one as well, but I'd love to have a big enough one where I can create life forms on demand. Ab initio. Say, oh, you want a different life form. The other technology that we're working on, I suppose I'm being really boring just about technologies I'm working on. I would like to make a true chemical configurable brain, and basically, and I think I know how to do this actually, because and make it conscious. And this will drive it. This is.
Are you talking about like an artificially constructed Boltzmann brain, something of this nature?
No. Boltzmann brains can't exist. Boltzmann brains are as ludicrous as I mean, creationists and Boltzmann and physicists who believe in Boltzmann brains, same thing.
Okay.
Because Boltzmann brain can't spring into existence because you have to have the lineage of all the brains going back in time.
I mean, I think even the math behind that specifically said, even Boltzmann said, yeah, it would be heat death of the universe before it would even exist anyway.
Yeah. There are some questions that are so ludicrous to ask. Just because you can write down the number doesn't mean you should ask it. And I think.
And for those listening, a Boltzmann brain is literally a conscious brain that pops into existence through random events.
Exactly, in the universe. And
in the universe.
And because there's no causal structure for that, it's just not. It's absolutely an impossible thing, right? And when someone says, "Oh no, in principle it's possible," no, it's just not possible. You want to be a creationist, but if you believe in Boltzmann brains, you're a creationist, and it's not an insult to creationists. You're allowed to imagine creation, but the thing I would love to be able to do is to make a chemical consciousness in my lifetime. Yes. And the way I would do this, now, how have we become conscious? We move around. Arguably, the most seminal event, and this wasn't my idea, I think it was, lots of biologists realized, when basically animals came out of the sea onto land, they could suddenly see for distances, and because they weren't going to be eaten in like a nanosecond or just a few milliseconds, they could see trouble coming. And so selection helped them invent basically cognition in a new way with time. So you can you remember the past, see the present, and anticipate the future. And if you've got a predator coming towards you, you've got some time to move. So this cognition, this movement with your brain allowed you to generate intelligence in a new way and ultimately consciousness. Now, how do you make an AGI? Well, we put a chemical brain in a robot and it has to walk around the world and just interact, like a toddler and just do stuff. I was like, that's really expensive. But if we could make a simulation, a metaverse, and attach the brain to the metaverse and move it around, we could probably build a consciousness in a physical form by having it wander around a metaverse. And that blew my mind because literally we are then creating brains in a simulation. The universe isn't a simulation, it's just that your brain is in the physical world, but everything you know is a simulation or a hybrid between you. So that would be something I'd love to create for fun, but I think that causes philosophical issues.
It's true. In a really simplistic manner, they've created a 1 hertz computer inside of Minecraft,
Yeah.
as in it actually functions inside, and they also created Minecraft inside of Minecraft. So some pretty interesting stuff there. Before we wrap up, where can people find you online?
They can find me on Twitter, just randomly making people angry. Although I'm actually not doing that anymore because it's no fun. But I am often trying to say, I just say random things. So I think it's at Lee Cronin, and you can find me on at Chemify, chemify.io, and croninlab.com.
Awesome, that's outstanding, Lee. Thanks so much. We have been standing on the shoulders of giants with Professor Lee Cronin. Thank you. I'm David Mackay.